This is day 85 of 50 days of tutelage, and in today's class, I'll be talking about gas laws. In physics, when we deal with gas laws, we actually take a different approach entirely because here we're going to be focusing mainly on measuring the pressure of a gas, the pressure of a gas, and not only that, we're going to be talking about the atmospheric pressure as well. We'll be talking about the atmospheric pressure, and also we'll be discussing about barometric height. Barometric height. So these three things are going to be our major thing that we're going to be doing in this under this topic. Fine, we'll still apply those gas laws, but we're going to be applying them a little bit different from what they used to be in chemistry. And so I'm going to be starting from the concept of atmospheric pressure. I've already explained a little bit about this in my previous classes. I already told you about the fact that we have a region of air that surrounds us, and these they tend to push on us. That push that they have on us is called the atmospheric pressure, and it is maximum at sea level. So if this is the sea level, the atmospheric pressure is maximum at sea level. But you can begin to have an increase in total pressure if you go down below the sea level. This atmospheric pressure begin to increase. So you have PATM plus rho GH based on the density of that of the liquid. And then if this begin to go up, you actually have a fall in temperature. You have PATM minus rho GH. And at a point in time, if you rise up enough, you can actually exhaust the entire atmospheric pressure, a point where you have zero atmosphere above the sea level. So we're going to talk about all these things in this class. Now, let me now proceed to something called barometric height. So what happened is that in physics, we like to always have a kind of unified way of doing things. And also, this unified way makes life easier when we're doing calculation. So if you're working with atmospheric pressure, you're working with gauge pressure, we want to introduce the concept of what we call barometric height, such that if I say the pressure of a certain whatever, I give it in terms of an height, and I reference it to a certain liquid or a certain fluid, then you already know you can remove all the whole process of density, you can move the process of having gravity there, and you just talk about the height only. For instance, you must have heard of the concept of millimeters mercury. You must have heard of centimeter mercury. Mercury is actually one of the most common fluids that is used in this situation. So what is happening here is that if I give you a certain pressure and I say it is 250 centimeters mercury, this is a barometric height, but it is also a pressure. So what this actually implies is that I'm only giving you the height in this case. Since I'm giving you as in terms of mercury, that implies that if you want to find the actual pressure in the pascals unit, then you have to multiply by the density of mercury, multiply by acceleration due to gravity, and then you convert this one to meter. Then you get the actual pressure in pascal. But we don't need all of those things. We know that density and acceleration due to gravity will be constant, at least for a given fluid. So therefore, we just stick with the barometric height only. So we're going to be dealing with barometric height in this place. So oftentimes the atmospheric pressure is always used with capital H, and the gauge pressure is always used with small letter h. Now let's now see how do we measure the pressure of a gas. We use a device called the YouTube manometer. The YouTube manometer. So the manometer looks something of this nature, and then we call it YouTube manometer because it is shaped like a U. It is shaped like a U. So let's so the gas we want to measure the pressure is going to be air, and then we have this limb open to the atmosphere. Of course, we have a liquid there. Like I said, mercury is always the choice. Mercury is always commonly used. Now, the first thing you notice is that there is a part in this chamber that is sealed, and there's the part in this chamber that is open to the atmosphere. Whenever you see the part that is open to the atmosphere, that part is always going to be the atmospheric level. So this particular place now that is open to the atmosphere, you can see that the atmosphere, the air that surrounds can begin to push down on this right here. So you call this one your atmosphere, atmospheric pressure. Then this level where the gas is, the sealed chamber, is going to be the level where you are actually measuring the pressure of the gas. And to get that, you're going to measure the distance. How far below this is it? How far below this is it? So you have this to this is your H. So therefore, the total pressure of this gas, like I've explained earlier, when you're going down, you sum it up. When you're going up, you subtract. So since I'm going below the atmospheric level, so you can see that this gas now is below the atmospheric level. The gas is below the atmospheric level. So because of that, the total pressure of the gas, the pressure of the gas is going to be the atmospheric pressure, which is this capital H, plus H. So had it been that this gas chamber now is above this atmospheric level, that would have to be capital H minus small h. And that's how we measure gas, that's how we measure the pressure of a gas with using a YouTube manometer. And the next one I want to talk about is how to determine the atmospheric pressure in a place itself. We use what we call a barometer to measure the atmospheric pressure in a place. So I'm going to be showing you how to actually construct a simple barometer. A simple barometer will look like this. It will look something of this nature. So we have a tube that is inverted into a container, and then we have fluid. Like I said, mercury is always the choice. We can use other liquid as well, but mercury is always the choice. So you have something like this. This is what a simple barometer looks like. Of course, the process of constructing this thing is by filling the tube, and you fill the tube with the same liquid that is here. So this liquid is mercury. So you fill the tube by the same liquid that is here, and you fill everything, like you fill the entire tube. Like the tube is like this initially, then you fill it up with the mercury, then you try to insert it into this place. When you can see some bubbles pop and all of those things, you try to like remove your finger, and then so that you can remove all the bubbles, then you insert it again. You do that all over and all over again until all the bubbles inside this place has been removed. After a while, you leave it, then you notice that this place was filled with mercury before. At a point in time, the mercury level is going to fall inside this tube, and it's going to maintain a constant height. So that's not really the important thing here. What I'm teaching is actually how to use the gas laws to measure so many things, not how to construct a barometer. So back to what we're doing. So in this situation, we have this place, the height of the mercury in this tube, the height of the mercury in this tube is going to give us the atmospheric pressure. The height of mercury in this tube is going to give us the atmospheric pressure. So when you measure the height from this place to this place, it's going to give you a certain height, and this is going to give you the value of the atmospheric pressure. So what do we mean by this is that every open place, I've told you already that every open place is always the atmospheric level. Every open place is always the atmospheric level. And then this place right here in this setup is the open place. And therefore, this guy here, if let's say a certain amount of gas is trapped in this place, and you want to measure the total pressure of that gas, that implies that from the atmospheric level to that gas level, it is going to be capital H minus H. Why? Because the gas is actually above the atmospheric level. And you already learned that when we move up, we do a subtraction. When we move up, we do a subtraction. However, there shouldn't actually be any gas in this place. This place is supposed to be an empty space. It's supposed to be a vacuum. When it has a gas suspended inside this, then you have what we call a faulty barometer. You have what we call a faulty barometer. So what I'm saying is that whenever you have a simple barometer constructed, and the barometer is going to be a good one that is going to measure properly the atmospheric pressure using this barometric height, then this chamber in this place has to be an entirely empty space, a vacuum. You cannot have a gas there. But once gas is trapped in that place, you can determine the pressure of the gas by using the fact that this level is the atmospheric level and the gas is above it. So therefore, total pressure is going to be capital H minus H. And that is how the barometer is like. Now, let's now see Boyle's law. How do we apply Boyle's law in this whole thing? Using a tube now, I'm not inserting the tube in anything, just ordinary tube. Using a tube, if I suspend mercury at a certain level in the tube, and by suspending this, let's say a gas is trapped here, a gas G is trapped in this situation. So there can be so many instances. It can be like this, and it can also be like this. So a gas is trapped in these three different occasions. So you have a gas here, you have a gas here. Now in this tube, you can see that we have the open space, and we have the sealed end. This place is open to the atmosphere, so the atmosphere is pressing around here. This place is open to the atmosphere, so you have the atmosphere pressing around here, and this place is open to the atmosphere. So what you notice here is that the gas in this place is below the atmospheric level. The gas in this place is below the atmospheric level. So if this is the atmospheric level, we call this one the capital H. And then the gas is immediately at a certain height, which is height H, below the atmospheric level. Let's call this H1. In this place as well, you have your H here, but the gas is above the atmospheric level here at the height. Let's call it H2. And in this case, you have the atmospheric level here, but you can see that this whole thing, they are at the same level altogether. So how do you now take the total pressure in this place? Total pressure in this place, so total pressure is going to be H. Now, since this gas is below the atmospheric level, you know that once you go below atmospheric level, pressure increases. So that will be H plus H1. For this second case, the total pressure is going to be H. Now you are going above the atmospheric level, so that will be H minus H2. And finally, for this one, the total pressure is going to be just the atmospheric level, because you're neither below nor above the atmospheric level in this case. The gas is just level up with the place where the atmospheric pressure is. And this is how you determine the pressure for each cases in this situation. Now, what is this? This is the length of the mercury column. This H1, H2, and H3 in this place, which does not really matter, they are the length of the mercury column, and this place is where you have the gas. So how do we now apply Boyle's law here? You remember that Boyle's law itself says that P1 V1 equals P2 V2. It's a relationship between pressure and volume, which is what? Which is actually inversely proportional. At constant temperature, we have pressure and volume are inversely proportional. And then so, since we're using barometric height in this place, let's say we're using the same tube. You can see that this tube, I just inverted them here. So this is the experiment 1, this is the experiment 2. In this situation, what we have here is I've been able to show you how to measure the pressure of the gas now. So what about the volume now? How do we take care of the volume? Volume is given as base area multiplied by height. I already explained this in the previous class as well. So if volume is taken as base area multiplied by height, you can say that this tube is the same thing as this tube, and it's going to have kind of a uniform cross-sectional area. A uniform cross-sectional area. So since it has a uniform cross-sectional area, it means that the area is going to be the same. So the only thing that is changing here is the height. So is the height of the gas. So let's call this Hg. So the only thing that's going to be changing here is the height of the gas, but the area is going to be the same. So the volume of this gas is A multiplied by Hg. So in this place you have P1 multiplied by Hg1, P2 multiplied by Hg2. But you know that it is the same tube, so therefore they will have the same area. Therefore, this A can cancel out. And what you have at the end of the day is P1 Hg1 equals P2 Hg2. And so in the first case, you have what? H plus H1 multiplied by Hg1 equals H minus H2 multiplied by Hg2. And with this, you can easily solve for anything that you are looking for in that situation. That is how you analyze pressure when you are dealing with uh, tubes like this and you're using barometric height. I believe that makes sense now. So the last thing I want to talk about in today's class, I will go back to that simple barometer that I spoke about earlier. So for the simple barometer, I've been able to explain that if you have your simple barometer constructed this way, so you have your mercury column here. That's a little bit higher than the previous ones. So the same similar thing that we did there, you can also find the volume of the gas. So if a gas is trapped in this place, you can also find the volume of the gas. Since it's going to be the same tube, so if you have like two different experiments set up, since it's going to be the same tube, you can just measure the height of the gas in the tube, and then you can use that as your volume, and you can use Boyle's law as well in this situation. It's still going to give you the same thing, but the only thing is that in this case, this is the atmospheric level. This is the atmospheric level, and the gas is above it, so you will always have H minus H. Please take note of that. Now you can transition from one barometric height to another. Because I've been using mercury now. What if you are given as water instead? Or you are using water and then you're given information about mercury. For instance, the atmospheric pressure is actually 76 centimeters mercury, or 760 millimeter mercury. This is the barometric height that corresponds to that of mercury. What if you want to get this thing in terms of water? All you have to do is to use the fact that we have rho GH, which is the gauge pressure in a certain liquid, is going to be rho GH in another liquid. So you can call this one rho 1 G times H1, rho 2 G times what? H2. So what will be varying is their density and their height. Their pressure will be the same thing in pascals. In unit of pascals, their pressure will be the same thing. So what will be changing there is just the density and the height. Of course, G is a constant. G is acceleration due to gravity. It is the same. Now, if you want to now convert this now, so let's say you already know the density of mercury, and you know the height here is 76 multiplied by 76. Density of water multiplied by H2, which is height in water. So with this now, by the time you multiply the density of mercury with this 76 barometric height of mercury that corresponds to the atmospheric pressure, and you divide it by the density of water, then you get the height that corresponds. So if it is 76 centimeter for mercury, it can be 200 and something for water. I've not done the calculation, so you can just get the density of mercury and density of water and do the calculation all by yourself. So that's basically how you can switch from one place to another. So if you're given a problem, you are given in terms of mercury, but what you're dealing with is water. You have to convert all the barometric height to that of water before you proceed. And so that is basically the major thing that you need to know about gas laws in physics. Of course, I could have discussed about other things about gas laws, but I will talk more about gas laws in chemistry. So let's wait for chemistry class so that I can give you more details about other gas laws, kinetic theory of matter, Charles' law, Gay-Lussac's law of combining volume, and all of those things. So that's it for today. Don't forget to like and subscribe to the channel. I'll see you in the next one.